Hope it is visible. Is it?
Yes, sir.
So we did all these things, and now the next module or this topic in this particular module is that how do we build a stream for pattern recognition, or for that matter anything you want. So we know exactly how to find optimal hyperplane for non-separating patterns. Just in the last class we concluded that. And the idea of SVM basically hinges on two mathematical operations for pattern recognition tasks. We'll see what are those. First one is nonlinear mapping of an input vector into high-dimensional feature space that is hidden from both the input and the output. So this lines looks very much similar to what covers theorem states, which we have completed in the last module, that is on radial basis function network. Now, once you have some nonlinear mapping you applied, next is construction of optimal hyperplane for separating the features discovered in the previous step. Means that is the after nonlinear mapping. So this process is exactly almost same what you do in case of this radial basis function network. But let's see how this thing can be achieved by SVM. And also the number of features constituting the hidden space is determined by the number of vectors, support vectors. Now this something is very different, which was not there in radial basis function. So by this time you know what do you mean by support vectors. And suppose this SVM theory provides basically an analytic approach for determining optimum size of the feature space. So which is not the case in case of radial basis function. And by default, if you go for as per radial basis function designing as per interpolation theory, so the number of this one, the dimensionality of the hidden space is equal to the number of data points in the training set, which is like very difficult to handle. And then we saw the practical ways how do you do that. This is basically a common way of applying SVM for pattern recognition tasks. So you have input space here, and then you have feature space or hidden space, what you call, and this can be done using some nonlinear mapping. That's why you can see here 5 is very much similar to what radial basis function we are doing that. And then we have some weight space here and with some bias. And this belongs to either positive class or negative class. This is your output space. This is how you do. So exactly this for the timing, this looks very similar to the radial basis function network, but as I told you that SVM provides an analytical approach that how many features should be there in the feature space. So now before we go about this, let's try to view our kernel as a machine. Viewed as a kernel machine. When I say kernel machine, so this is something to be looked into, and this is a bit a very simplified approach, or you can say that, or some sort of, you can say that it's a trick, you can say. So suppose X is one particular example from a larger set X, and also X is of m dimension. This is what I mean to say. And you have this phi j equal to 1 to m1. It basically is a set of nonlinear transformation from input space to the feature space or hidden space, what you call. So remember that the notation which you adopted during the last module, that is in radial basis function network, that m0 indicates the dimensionality of the input space and m1 indicates the dimensionality of the hidden space. So as per that particular, this one we are doing this. So let's say we have something like this, and we make an assumption that phi j is defined a priori for all j. So this basically, if you are ever taking any sort of the function, this radial basis function or anything of that matter, it should be defined up. We are not going to compute on the fly. So when we have such a transformation, then we can define the hyperplane acting as a decision surface, and which is in the output layer, of course. So you have j equal to 1 to m, wj phi j x plus b 0. And this is whenever you find a hyperplane, you have to compute this part and equal to 0. So where, of course, this denotes a set of linear weights connecting the feature space to the output space. So this looks very much similar what we have done in the radial basis function network. That's what I told you, that SVM basically is a very generic machine which can be configured as to work as a polynomial machine, or it can be configured to work as a radial basis function network, or it can be just like a MLP as well. So we'll see that. So we can write this equation, above equation. If you subsume this and j equal to 0 to m1 instead of j equal to 1 to m1, just to simplify the equation, that nothing more than that. Here W0, we know that when bias is which applied, weight space W0 is as good as bias, and the input is nothing but is clamped at 1. So this is what it does. Also, it defines our decision surface computed in the feature space. So let's say this. So when we define a vector, so something of this form, and as you know, these functions you already defined. So phi 0, phi 1 till phi m1, and by definition you will be always seeing phi 0 equal to 1 for all x. This what is meant by because of clamping bias input as a 1, because the bias we want to use as a W0. So that's what, just to indicate it. And this vector phi x represents the image induced in the feature space due to the input vector x. So image means, it's simple to say, there's nothing but a map. When we say image, it's nothing but the map. Okay, so mapping function, you know, right? So using that only, you can say it's a map. And when I say image, literally don't think about this images, this photo, that photo. No, basically means if the input is given, how it's mapping to. Now in terms of this image, or you can say this some sort of function or map, we may define the decision surface in the compact form, something like this. So instead of writing like this one is an inner vector, inner product, so which we can write in terms of vector. Wj is a vector, phi j is a vector, and this is what has been done here, right? We are writing this. Now when we adapting this particular equation to our situation involving feature space, where we seek linear separability of features, we are looking for something like this. Now what we are doing that here in the conventional SVM, when we didn't apply any non-linearity, this is the what it cases. When you apply this kind of mapping or the image, so instead of just x, it be replaced by phi of x, right? Everything remains same. And this which we have seen, which we got it by applying the first condition on separating finding the optimality for the linearly separable case. And we may define the decision surface computed in the feature space, something like this, because you have WTX, you know, WT phi x equal to 0. W, we are defining something like this. So when I say WT phi x equal to 0 to find the decision surface, so here one t will be there, because there's no fun in or logic in using t over alpha and di, because they are the scalar values. So vector is only phi, so phi x t and this phi x. From that particular logic, we can say this phi t xi phi x equal to 0. Okay. Now, so this is the equation of the decision surface. Now this term is very important here. So phi t xi and phi x basically represent the inner product of two vectors induced in the feature space by x and xi. Phi may be same, but inputs are different, so accordingly the map will be also different. So for this, there is something called kernel trick, and kernel trick is something like this. We define this multiplication of actually these functions are in terms of SVM, or in earlier in the last module we used to call them as a radial basis function. Here we call them as something called eigenfunctions. Eigenfunction. So you might have learned, or probably while reviewing the linear algebra, I talked about those things: eigenvalues, eigenvectors. Like that, you have eigenfunctions. So we define an inner product kernel by this one. So we say phi t xi. And when you open it up, so j equal to 0 to m1, phi j x and phi j xi. So two vectors you're talking about, one is x, one is this xi. Now here I is only changing, and that is n number of times, mean how many data points are there. So this is what it means to say. And this is fixed because number of functions are equal to m1. That's why this is j equal, j is varying from uh, actually it should not be 0, it should be 1. There's a typo here. So basically if it's a typo if you consider without bias point, but if you consider the bias point also, because phi of 0 we have considered is always +1, then in that case this is true. And this I equal to 1 to n, total number of examples in the training set. Now kernel is formally defined as, so kernel is a function that computes the inner product of the images produced in the feature space under the embedding phi of two data points in the input space. Basically nothing but the inner product of two images, that's all. And you define which kind of embedding is, or the function mapping has been applied for those images. Now some properties are there for this, because this function is symmetric about the center point xi. That is, either if I can write k of x xi, or it can be xi of x. Why I can do this is because here it is inner product only. So I can always swap the position. Here I can write phi t xi and phi x, that's all. So either I write x xi or write xi x. It doesn't matter. Overall it's inner product, and overall the product value should not change as long as it doesn't happen. So this particular function is, or the kernel is symmetric. So that's why k x of xi equal to xi x, and this valid for all xi. And its again is maximum value at x equal to xi when both are same. And total volume on the surface of the function is kxxi is basically constant. See that? Now the people call it something called kernel trick. So we'll see here whether this trick is, what is this trick and why we are doing it. Let's see. So as far as pattern classification in output space is concerned, specifying the kernel is sufficient. We don't have to worry too much. We don't need to explicitly compute the weight vector W0. Due to this reason, the application of this one is commonly referred to as a kernel trick. And what it is, just hold on. Remember that whenever you have something of this form, and remember that here T I have not applied because you are finding the inner product element by element product and then summing, which is when I say T, this is not in this notation but in vector notation only. So what this kernel trick is that whenever there is some relation of this kind, phi t j, phi j, so this becomes a kernel trick. Then instead of writing this, we can just write k of x. Then you may doubt, yeah, how does it help, or how does it simplify my life? So we'll see that. So even though we assume that the future space could be of infinite dimension, the linear equation, this what we are saying, anyway, this is equal to 0. Defining the optimal hyperplane, because we said that, remember that now. Earlier we used to say Wt phi x equal to 0. That we now wrote in terms of k, and then we are saying I equal to 1 to n L phi di k x xi equal to 0. Now defining the optimal hyperplane consists of a finite number of terms that is equal to the number of training patterns used in the classifier. So we'll see. So SVM, when designed with kernel, is known as kernel machine. So many of you might have some sort of exposure or prior idea about the kernel, changing the kernel, applying the SVM, though you really don't know what is happening, why to use kernels, what will happen if I choose a different kernel. And first of all, why kernel has to be used at all? Without kernel also I can design. So those kind of queries should be answered here. So here, let's say for pattern classification, the machine is parameterized by an n-dimensional vector whose ith element is defined by this particular product L5 di. Now this can be viewed as a jith or ijth element of the symmetric matrix, this one. And how do you find it? That we'll see. Where K is a non-negative for a definite matrix or kernel matrix, or simply we can say that it should be minimum positive semi-definite matrix, and it is always the case. And K is a kernel. The kernel matrix is a PSD, that is positive semi-definite. So it should satisfy this property xtkx, right? And this value should be greater than 0 for any real vector x whose dimension is compatible with K. Now there is something called Mercer's theorem. Now the question is, man, it is so good. So let's say some reason. Then why cannot we apply? But before that, we should know that whether any function can be taken as a kernel. No, only few functions which satisfy certain property are called kernel, and those particular properties are nothing. They are stated by Mercer's theorem. So what Mercer's theorem says that let's say x and x prime be a continuous symmetric kernel that is defined in the closed interval a and b, and likewise for x prime as well. Now the kernel xx prime can be expanded in the series. We can write it as it is, something like this: j equal to 1 to infinity lambda I phi I x phi I and x prime with positive coefficient something greater than 0 for all I. Now for this expression to be valid and for it to converge absolutely and uniformly, it is necessary and sufficient that the condition so and so a to a, b to a, b to a, x prime phi x prime dx prime, this value when I take something like this should be greater than or equal to 0, and it holds for all phi I for which we have, for all those sorry, psi, not phi's, for psi we have this kind of relation that it should be a finite energy. This is square dx also together less than infinity means it should be a finite energy. Now let's see based on this what we can infer. So feature x phi I, this is as I told you earlier, we call eigenfunction of the expansion, and lambda I is the eigenvalue. So in this, these are the eigenfunction, these are the eigenvalues, and we know eigenfunctions, eigenvalues. But eigenfunctions, if you want, is you can say that an eigenfunction is nothing but eigenvector that is also a function. So basically it's eigenvector, but at the same time it is function as well. Thus an eigenfunction is an eigenvector, but an eigenvector is not necessarily an eigenfunction. And you can just go through the link if you want to understand further. So the fact that all eigenvalues are positive means that kernel is positive definite. This is what you have to ensure. That will come to know from the eigenvalue itself. So Mercer's theorem tells us whether a candidate kernel is actually an inner product kernel in some space and therefore admissible for using SVM. Also, Mercer's theorem says nothing about how to construct those functions. It just says that if something is function is there, I can check whether it's a valid kernel or not, but it does not give any idea how do you construct it. It's just like Shannon's Claude Shannon gave this idea that through his first paper on this mathematical theory of communication, that the code should be there used for reliable transmission of the information over the noisy channel, but he did not tell us how to construct those codes, so people had to find it the way to do it. Likewise here also, Mercer does not tell how to design those functions, but it says that if function is there, satisfies so and so properties, then it will be a call a kernel. So now we'll see that how do we go for design of support vector machine. So first of all, this expansion of this kernel permits us to construct a decision surface that is no linear in the input space, right? And how no linearity, that will be defined by the phi itself, but whose image in the future space is linear. Image in the future space may be linear as well. We may state the dual form for the constraint optimization of SVM as follows. So dual form, we know that. So first we'll try to, so this is dual form. So wherever this xi, xj was simply there, we are replaced with k, xi, xj. Here some sort of inner product was there between xi, xj. So we wrote something like this. Okay. And this is the condition. This condition we got from the primal problem only. And this is also condition from the dual problem. When C is to use a specified constant. Now there are some examples of SVM. So the SVM means, example means here for a different kernel, which you choose this kernel, how your SVM is working. If you choose different kernel, how your SVM is working. Okay. So first one is that if I use this kind of kernel, means for a k, I use something like this. Okay. xtxi plus 1p. And then the kind of machine which I have. So this is called polynomial learning machine, where P you can choose from. Okay. And second is the radial basis function network. Here you see that basically it's to what would you say? It's a Gaussian function only, Gaussian radial basis function. And width sigma square common to all the kernels is specified a priori by the user. They already tell you. Then if you want to design a two-layer perceptron, then your kernel you change to this one. 10 hyperbolic with this value. Consensus theorem is satisfied only for some values of beta naught and beta 1. That can be checked on this. So it is not surprising when we started this SVM, we said that, okay, this is not a particular machine, but a generic machine which can be configured as a polynomial learning machine or a RBFN or a perceptron. So this inner product kernel for polynomial and RBF type of SVM satisfies Moses theorem. And for all three machine types, that is, which is stated above, the dimensionality of the future space is determined by the number of support vectors extracted from the training data by the solution of the constraint optimization problems that we see. And SVM avoids the need for heuristics often used in the design of RBFN and MLP. So remember that in MLP we were saying that is designing an MLP where that is with backpropagation algorithm is a more an art than science. What they mean to say that prior experience for designing MLP works quite handy over there. But here SVM versus kind of heuristics, so you can do it directly. Also, in RBF type SVM, the number of radial basis function and their centers are determined automatically by the number of support vectors and their values. So which is not the case. Then you have to find all centroid and those centroids using those concepts, and those are your center for the radial basis function. But here everything is automatic. So basically, SVM offers a solution to the design of a learning machine by controlling model complexity, and which is independent of dimensionality. Whatever the dimensionality may be there, is try to control the model complexity. So what do you mean by this? So first of all, there are two aspects here. So first one is conceptual problem. So that is dimensionality of the feature space is purposely made very large to enable the construction of a decision surface in the form of hyperplane inert space. So this is working most of the cases, and that we'll see. Second is for good generalization performance. The model complexity is controlled by imposing certain constraints on the construction of a separating soft margin hyperplane. which results in the extraction of a fraction of trading data as about vectors. We'll see. So first one is conceptual problem, another is a computational problem. So computational problem, the need to compute the weight vector and the bias in the output layer of RBF network is avoided by using kernel trick. I hope one example I have, if not now, I'll show it here later also. I don't remember where I kept it, but just a minute. Just give me a second. Let me just check it out where I have kept it. Just okay, so here I got this example. Just to give an idea, what do you mean by kernel function and why we are saying that it is better at computing? Because in this I'm talking about this. We just said that the need to compute the weight vector and the bias in the output layer of the RBF network is avoided using a kernel trick. Kernel trick we know, but the how it works like that. So just a minute, here we see. It is visible. Hello. Okay, so we'll see this. So okay. So the first we'll a little talk about this kernel function. Little I'm taking digression just to get an idea that how using a kernel trick basically helps to speed up the computation. See here. So first let me talk about it briefly that a kernel is a shortcut that helps us to do certain calculation faster, which otherwise would involve computation in higher dimensional space. So simple to say that is some sort of trick which helps us to do faster computation, which is required in the otherwise required in the higher dimension space. I'll show you with a demo. Demo means numerical demo. So mathematical definition of this one is nothing but there are two functions are there. Earlier I'm taking was phi, yes, the fx and fy, and this is nothing but inner product. So k is the kernel function, so this is just defined like this. Don't worry about it. So what's the intuition behind this? Is something like this. Normally, when you calculate the inner product of x and y, let's say these two are m is much larger than n, require us to calculate fx, fy first, and then do the dot product. Means first x is given to you as a vector, y is given as a vector. So first you'll be computing f of x, f of y, then you'll be computing the inner product. Okay, this is what normally does as a kernel function if you go this way. Now let's see this. These two computation steps can be quite expensive as they involve manipulation in m-dimensional space, where m can be a very large number. Means y first mapping, first finding the image of the vector, then find the inner product between two images. It may very computational intensive assignment. So let's see here. But after all the trouble of going to the higher dimensional space, the result of the dot product is really a scalar. is a scalar value. You'll be surprised, what nonsense is this, man? You are projecting into higher dimensional space and you're finding the inner product, and the inner product is a scalar value. Then what's the logic behind going for this higher dimensional space? So we come back to the one dimensional space once again. So why we are doing all these things? So hold on for a minute. Now the question is, do we really need to go through all the trouble to get this one number? Definitely not in this way. So do we really have to go to m-dimensional space first of all? So let's see this. So the answer is no, if you find a clever kernel. If you find a clever kernel. So it's in this one particular statement, this intuition, I kept it a different color just to give one by one the idea how we are going to do all these things. So it says that if you want to find this kind of inner product, let's say only phi x and phi t and phi x, then you have to map it, then you find the inner product and do all those things. You don't have to do is provided you have the right kind of kernel with you. And let's see this. So this information for this particular slide, this particular intuition, I liked it from Lily Jiang's blog. Basically, I took it. And so this I'll show you with an example how it happens. Let's say very simple to say, I've taken a vector x, which is three-dimensional, another vector y, but that is also three-dimensional. Then the function, let's say this is your f of x is basically a function defined. It is some sort of function it is. And if that is the case, which is defined something like this, the kernel is, we know that xy, let's say kernel is nothing but inner product and square of this. Now in order to find this, what you have to do be, now simple, I'm trying to put it across. The x is 1, 2, 3, y is 4, 5, 6. Right? Now you have to find f of x. F of x means wherever this x1, x1, then x1, x2, x1, x3, all those things are there. Multiply, keep all those points, and then just to find f of x, that is like this. If you do this, you have this kind of value by applying this particular function. I have this value. And of course, when you do this manually, you'll be surprised. It takes a lot of time. And for f of y, you have this kind of thing. Okay, to this only. So you have this kind of techniques or method. Now we have found f of x, we found f of y. Now let's see what. And sorry, here it should be f of x comma f of y. There's a typo, square. So anyway, let me find a kernel only, just a kernel. If finding the kernel is there, so in this case, between this and this, we are finding the inner product, right? 16 into 1 plus 2 into 40 plus 3 into 24 plus 2 into 20, all these things. We are finding the kernel. That is 1024. So you saw the process. How do you do all this stuff now, right? So a lot of computation because we are going from 3-dimensional to 9-dimensional. Actually, this was 3-dimensional, and due to f, you are going to 9-dimensional, right? Now it is 9 terms are there, 9-dimensional. And finally, when you multiply this, all this 9-dimensional, etc., becomes only 1-dimensional. So let's see that if I have to get this value only, why I have to take such a lengthy step? Kinda, is there any possibility to do this short span of time or quickly? So now let me talk about a kernel. The kernel says that if you have this kind of kernel, there is x and y inner product and square it. So instead of doing something like this, and then you are getting the value, if I have a kernel of this form, so there was no typo as this was, instead of doing something like this, if I have that kernel, so now somebody found, okay, instead of doing this, directly take this in square. This is as good as doing like this. So that's what I was saying. You can do this calculation faster, provided you find a smart kernel. So smart kernel is this here. So you just take the inner product of this one, basically 4 into 1. So 4 plus 10 plus 6 into 3, 18. square it, and you will find that, oh my god, beautiful, I got 1024. Instead of doing this mapping, and finally this, I can do this same result if I'm getting, and definitely this computation is far faster as compared to this one, isn't it? Yes or no? Any question here? This is very important and very fundamental question. Then if somebody asks you to show how a kernel may, by using kernel trick or kernel, the computation become faster. So this, the idea is given here in this particular slide. It's very important slide. Unfortunately, this explanation is not given in a majority of the books on neural network or this one. So out of my curiosity, I just looked here and there reading many blogs, and finally I found a suitable answer for this. So the people say it happens, but how? So nobody has demonstrated. So this is what is happening, and it's a very simple and succinct example that to show that. And when I was saying that finding the smart kernel means if this I have to calculate, what is the equivalent, I can find it out. And now the question is, this one will keep on varying, so this also has to vary in order to find the equivalence between the two. So the same result, but this calculation will do much faster. The word kernel is used in mathematics to denote a weighted function for a weighted sum or integral. Okay, this is what we mean by kernel. And of course, in operating system, you have different meaning altogether. So that's all from this part. Okay, now let's get back to this one. So this, when I said this, this what I was talking to. Now on this one problem, I'll just visit. Just I'll take a 5-minute break and be there. I'll just come. I'll just be there before I start the example. Be there. Yeah, we'll start now. So the problem which I was talking about, that how do I apply SVM to a how do I show this? Sorry. To solve an non-linear classification problem. And why focus on non-linear? Because if you can solve non-linear, linear is straightforward. So we are going to take this value. So instead of saying 0 and 1, the values we are labeling as a -1 to indicate 0 and +1 to indicate 1. And of course, there's a reason behind it that you'll come to know here, because symbolically we are using it to represent 0 and 1. So this is the XOR problem as you know it. And we also know that it's basically a symbolic nonlinear classification problem. So we'll see how we are going to do this. So for this, a kernel is given to you, which is given by, as defined by 1 plus xt xi. So this kind of kernel, if you remember, what kind of machine it is when you have taken a kernel of this form, what kind of machine you call it? Is it RBF? Is it MLP? Hello? Just now you've seen some time back I was talking about the kernels, different type of kernels. So basically this is nothing polynomial machine. So here we were discussing this. This one is a polynomial learning machine. Any one of them you could have applied and solved. I am just showing with this, if you use this particular kernel, then whether you are able to solve XOR problem or not. But by using any of this, you should be in a position to do it, right? So we'll see now. We have this particular kernel, and for that we'll just try to find, we'll write, say x is say 2 element, because XOR problem their input vectors are 2-dimensional, so x1 xt, and here just to represent is a xi. So xi is the name of a vector. So xi1, the first component of this xi, second component, we can write xt xi. This one is nothing but x1 xi1 plus x2 xi2, right? And now when I substitute this one here and expand it, then it becomes nothing but a plus b plus c whole square. So a square plus b square plus c square plus 2ab plus 2bc plus 2ca. And from that particular logic, we get that particular expansion, we get this formula. Okay. Now when you have something like this, I want to extract the eigenfunction out of it. So we know something like this, that kxxi is nothing but phi xt, phi x. If that is the case, and this is equal to this entire part, so we want to know what is that phi x is and what is phi xi. Of course, both are same but different as per directed by their respective vectors. So we have to rewrite something like this. So from the whatever the statement which is given the previous slide, you can write phi of x in this particular form and phi of x this way, because if you apply like this, that is phi t and phi xi, you'll get the same expression what you got in the previous slide, this one. Once you have this, so here of course I is varying, so that is basically this is indicating the different inputs. And the current problem of XOR classification problem has got 4 inputs combination. So we have something like this. Now when we go for this, so we have to compute this kernel matrix. As I told you, kernel matrix, that is ij equal to 1 to n, where basically n equal to 4 in the current problem, because XOR the problem we have 4 combinations possible. So accordingly we'll be finding this kxi xj. Now when I see kxi xj, we have to rewrite those formula in terms of xi xj, because this is written in terms of x in xi. Then we have to write in terms of xi in xj. So this probably I have written here. We'll see. So as I mentioned here, this xi equation is the whatever we have started, and which we can write for sake of easy calculation of this kernel vector, or sorry, kernel matrix xi xj. So wherever xi is there, that will be represented by two component xi1, xi2. Wherever xj is there, this will be represented by two component xj1, xj2. So idea remains same, and then we have something like this. Now the question is what it is this. So by taking this one, by taking this 2, so suppose my xi and xj. So xi xj is nothing but what should I say? Xi is -1 -1. That is the first input. That is 0 0 -1 -1. Xj is -1 and +1. From that you are doing. So whenever it is xi or means x1 x1 x2 x2 x3 x3, when you do this computation, you will see that this one, the value comes out to be uh, 9. So I'll show you, but before that, just let me note down this equation so that I can use the board to show you at least one combination. Just a minute. So kxi xj 1 plus, here I have to do double work, but okay, xj1 square 2xi1 xi2 xj1 xj2 6 2 square xj2 square plus xi1 xj1 xi2. Okay, so let's see, let's do it now. The board. For this, let's take this value. First, we'll try to find for 1 1. There is a -1 1. Yes. So start. Yeah. So let me write this formula once again here. There is kxi j 1 plus xi1 square xg1 square plus 2xi1 xi2 xg1 xj2 plus xi1 square, sorry, xj2 square plus.
So you're not audible to me.
Okay, am I audible to others? I have not
Yes, sir, now.
started. Okay, I was not speaking anything. I have
Acha,
just.
sir.
Okay.
Okay.
That's 2x I2 xj2. Now, this was the case, and the first case which we are talking is like x1 case, that is -1 -1 combination. And let's say x2 is -1 +1. So let's first try to find out the case of x1 1, what I mean to say when I take this and this. So we'll substitute this. So here, now here this is I1, this is I2, this is J1, this is J2. But when I say x1, x1, so J accordingly everything remains same. So we'll just try to see 1 plus and C square. So it is 1 into this is also 1 because j is also x1 only, plus 2 into -1 into -1 into -1 into -1 plus 1 into 1 because due to square plus 2 into -1 into -1 plus 2 into -1 into -1. So this comes out to be 1 plus 1 plus all these minus 4 minus are there, so this is plus only, so 2 plus 1 plus this minus minus plus, so this is 2 only, this minus minus plus, so this is 2 only, this is a 2 4 5 7 8 9. So you found out k11 is 9. Now let me check what is k12. Basically this was k12, right? This was x1, this is x2. So it means to say x1 comma x2. So now we'll start doing. So little circus is here now. 1 plus xi1 square, any this square means 1 into xj1 is also -1, so that is square, that is 1 plus 2 into -1 into -1 into 1 because xj2 is +1, so 1 plus this is 1 into 1, no problem. Here 2 into -1 into -1, no problem. 2 into xi2 is -1 but xj2 is 1. So due to that values will change. Now 1 plus 1 plus. Now here the number of minus are odd. So basically this becomes -2. -2 plus 1. And this minus minus plus. So this remain where I am plus 1. So this becomes 2. This is minus. So this becomes -2. So you see this will go. This will go. The value comes out to be 1. So this you can check for any combination and you will see that only the diagonal elements, whether I take 2 2 or 3 3 or 4 4, in this case it is 9. Any non-diagonal element ij here, if I say the value is 1, as long as I is not equal to z. So any combination here, this value comes out to be 1, and I have shown the computation also, so you should not get confused. Now, so don't expect that the same question I'll be asking in the exam. So you can expect a classification problem, a no linear classification problem, and it will be given to you, and you have to find the kernel matrix accordingly, following the same process, and do the rest of the calculations. So that we'll see now. Okay, so let's see. So here we do all those things we have done. So kernel matrix is found. Now kernel matrix is found. So how do I solve all this duality problem, whichever we discussed and all those things? So here we go. So objective function for the dual problem is given by this. So remember alpha 1, alpha I, alpha j, which I really don't know. Di dj is known to you. Di dj is nothing but this one. These are di, means if this is the I, this is minus. If it is j, this is +1. So likewise. So and k, x1 xj, this you got from this particular matrix. So we'll try to see. And this expansion is due to this is quite overwhelming. So don't get confused over that. It's very simple, straightforward. So this is straightforward. So I'm just expanding it. So this you go across. So 1 equal to 4. So I've written same. -1 by 2. And here basically two summations are there. So it's just like 2 loops, 4 loops. So you follow all those things. So I've gone step by step. So you get something like this. Okay. And then we so after substituting the value, you feel that there is some possibilities there. I can combine this all together. So this kept it, and some of them are double. Suppose alpha 2 is there, so we have clubbed together. So alpha 2 square, alpha 1 square, etc. We have written this. Now after that, you substitute the value for all this alpha, all d's and k. because those values are there with you. What is not known is alpha. So everything, entire equation should be in terms of alpha, and function is also in terms of alpha. You should be in a position to differentiate it. So you have written something like this, and substituting Kij from kernel matrix and all those things we get. So same equation I've written it. Now after substituting this d and k value, we get something like this. Once we have this, something like this, and there are four Lagrange variables here, four Lagrange multiplier acids. So I have to differentiate it 4 times with respect to each of those alphas. So once we differentiate and equate to 0, they yield this particular result. So this 4 set of equations, you get it, right? 4 set of equation you write in the matrix form in this way, and you get something like this. And when you see here, so you find that optimal value of alpha 1, 2, 3, 4 is all values comes out to be 1 by 8. So remember that alpha, if it is comes out to be 0 for some for any particular component, it means that that particular data point is not a support vector. Now, if the alpha value for whichever the data point it is non-zero, it means that those data points are support vectors. So this is clear indication just to knowing that how many support vectors are there. Here 4 Lagrange variables were there. All 4 has got non-zero value, that is equal to 1 by 8. This indicates that in this particular example, all inputs are vectors are support vectors. Okay. Now, so here's the question. So what's the big deal? Now we substitute this value of alpha in this particular equation. When you get the value equations, you get the objective value, and this value comes out to be 1 by 4. And correspondingly, we already know that this is simply 1 by 2 W naught square from the starting itself. If that value comes out to be 1 by 4, so W, this one is, you take all these things, and this square goes over 1 by root 2. And then because we know that W naught, because you got this alpha etc. from this, and W naught is known to you, and W naught was given by like this, and also it is alpha 0 di. Instead of saying alpha, I may say alpha OI, that is optimal value, di phi I. Phi I, you'll be surprised at why we have used all these things here. We are not using anywhere. Here we are using phi, which you already calculated in the starting. I was saying, right, that this is the phi. This is the phi. So in your final this one, di is known to you for each one of them. You substitute all this by phi calculation, all these things. This is the value. So that is the weight vector. So weight vector you found means all 0 except the third element, that comes out to be minus root 2. And based on that, this is equal to 0. So you have this weight vector, and phi x you have equal to 0, which reduces this final to minus x1 to x2, which is equal to 0. And this when you substitute this, so it is as good as this kind of a system comes out to be 1 and this one. So, and because minus was there, multiplication has to happen and minus has to be multiplied. So see that by doing so, what happens whenever this is, now see that it is exactly, it solves the XOR problem. And so whenever this is minus, minus, minus plus, and this is minus, so the value comes out to be minus. When both are different, this can to be accordingly the value, this things have to be remain same. Now based on this, it solves this particular problem. So this is how a SVM can be designed for any given particular problem. So that you can expect that you'll be asking to find a equation for hyperplane. The hyperplane equation in this particular case is nothing but this, minus x1 x2 equal to 0. So this is a simple hyperplane equation for this particular problem, that is the XOR classification problem. Includes your SVM. Some of the part here I have skipped, that is a Vichy dimension, which is very important. And the reason behind that is that there is something called statistical learning theory. You need to have that kind of background to understand what you mean by Vichy dimension. So that part I have skipped for the time being. We'll see if later time permits. So this concludes your SVM. And so yes. And in a couple of minutes, you will be getting your quiz. So be there. Be there.